All right. Thank you, everyone, for joining us today for Akka Days. As many of you may know, Akka turns 5 this month, so we're celebrating with a series of webinars all about Akka. We have the honor of some excellent presenters joining us. First on the docket is going to be Duncan DeVore presenting Deploying Akka Persistence. And immediately after him, we're going to be joined by Machacek and Lashford from Cake. Then they're going to be presenting tuning and monitoring Akka. So tomorrow, just so you know, we're also going to have Derek Wyatt, who's going to be presenting Deploying Actors, Await, and Akka Clustering. And then we'll wrap things up right afterwards with Mike Nash's presentation on do's and don'ts when deploying Akka in production. So before I hand things over to Duncan, just wanted to go over a couple details. All of these presentations are going to be recorded and made available on our YouTube channel. So if you need to hop off at any point, feel free, and we'll be sharing the recordings with you immediately afterwards. And if you have any questions throughout the presentation, please just insert them into the little chat box in the lower left-hand side of your screen, and I will respond to things as they come in, and if there are some good questions that we save for the end for Duncan, we'll make time for a Q&A. We're going to take a quick break right after Duncan's presentation, just a minute or two, so that we can make sure the next speakers are all set up, and then we'll get started hopefully right at the top of the hour. So with that, I'm going to hand things over to Duncan. Duncan, thanks for joining us today.
It's good to be here. Thank you, Laura. So my name is Duncan DeVore, and I'm going to have a talk today in regards to Akka persistence and some of the lessons that we learned, what kind of led us down that path, so to speak. And so let's go ahead and get started. Oops. So this all started roughly about 3.5, 4 years ago, and we were presented a pretty significant challenge. We had the requirements given to us for an application that we needed to design in the energy industry. And the goal was a fairly lofty goal in that we wanted to be able to take what has historically been considered an expense for the industry and turn it into a revenue stream. And in order to do that, there were a lot of different things that we had to consider in going forward. And the base, or the client base, was essentially commercial customers. So manufacturing factories, data centers, universities of this sort. And what we wanted to do, as I had mentioned, is we wanted to take this thing that was typically an expense and manage it for our customers such that they could turn it into a revenue stream. And we could do that in two ways. One was essentially by curtailing what is known as their load, their energy usage, cutting back, if you will, so they would spend less on energy. And the other was accessing their energy assets that could generate energy and bid the results of that excess energy that they generate into the wholesale market so they could make money. And we had a couple philosophies on how we wanted to do that. The first one was we wanted to be able to give them business intelligence through forecasting. So through various algorithms, we would go ahead and say, hey, this is what your energy consumption is going to look like tomorrow or over a certain amount of time. And the other way was to actually access their assets directly as a result of the forecasting and make decisions for them. And that is relatively complex because the different energy assets that comprise their footprint, if you will, they have an interrelationship with one another. So it's not as simple as just saying, here's an asset, let's do something with it. We have to take into consideration how the assets play with one another. So through that process, we kind of nailed down what we wanted to do. The types of assets would be renewables, which are solar and wind, storage, which could be batteries. But interestingly enough, things like a building or a chiller or something like this could also be looked at as an item that could store energy and be tapped into. And then ultimately the idea was if the customer so desired, we could directly control those assets. So one of two ways: we could provide them with the intelligence, and they could go ahead and control the assets themselves, or through a direct pass-through, we could control the asset. So 4 or 5 years ago, as with lots of applications that are built today, we started out and we chose more of a traditional monolithic approach. We used the tools at hand that we had. Essentially were Java and Spring, Hibernate. We had some Scala involved. I had been doing a lot of Scala prior to this. We had the typical RDBMS's Postgres SQL Server was what we chose at the time. And as we developed the system and pushed it out, initially it started working rather well. But as time went on and we started gaining a whole ton of data, hundreds of millions of records, the typical problems that you have with this type of structure began to occur. So deployment became more complicated because we'd have to deploy to multiple servers. The responsiveness of the screens started to become a challenge because you're using a relational model in the background and you have queries that you have to continue to optimize. Scalability became a problem, and things like cascading failovers with our deployment mechanism were of great concern. One of the key things, though, for us was auditing. So because it was the energy industry, auditing is very important. And with this type of model, it ended up becoming quite difficult. Auditing was an afterthought, if you will. And so for our particular scenario, we ended up using NVARs from Hibernate. But every time some new audit requirement came up, we had to go back in and we had to modify the code and take care of these things. And then ultimately the thing that concerned me was eventually load in the form of what we call meter data. Each client would have meters that we would read, and they could have several meters, 10, 20. We would pull those readings in every minute. So you can do the math, 10, 20 meters per customer, several hundred or 1,000 customers, it becomes a pretty big mess fairly quickly. So we ran with that solution for about a year, but during that whole process, consistently in my background is there had to be a better way to do this. There had to be a better way to build an application so those typical concerns that you're up late at night about or whatever, that you no longer had to worry about. So what we did is we got together as a group, we sat down, and we began to think through this. What is the way we want to handle this? How do we want to handle it? Akka was just coming out at the time, and I was familiar with Scala. One of the things that I had kind of learned from my previous experiences was trying to keep everything modular, more along the terms of like a microservice kind of scenario. So I really wanted to embrace that when we went to redesign the system. I wanted it to be very loosely coupled. I wanted it to be message-driven, and as a result, or event-driven, and as a result, be scalable. I wanted fault tolerance. All these ideas, I wanted them to be part of the way that we designed and build the application, and of course, responsiveness. And one of the key aspects, because I had dealt with concurrency quite a bit previously, is I knew that if there was a way that I could make the domain model immutable, that would, from the get-go, that would help quite a bit in resolving those types of issues for us. So that was one of the key things that I wanted to address, which ultimately led us to Akka Persistence. So, and then we also wanted to have a schemaless database because previously we used Liquibase and tools like that to drive out our database changes and stuff, and I didn't want to have to worry about that this round. So what we did what everyone who embarks should do, consult the vendors. We went to meet Mongo and had some great discussions with them, and we called Typesafe and had them come on site and kind of review what our ideas were, give us some tips and pointers on what we should do. And that's where I had mentioned I wanted to have this immutable domain model, and the notion of event sourcing came up. And at the time, I didn't really know what it was, but I said, hey, if this is going to let me build an immutable domain model, then it's definitely worth giving it some serious exploration. So as we began to push out our version 2, some of the key design decisions that we made were, first, obviously we wanted to follow domain-driven design. We'd had great success with that over the years. A schemaless model for the database, an atomic microservice type-based architecture where we could spin things up, that they would be, they could stand on their own, they were fairly easily testable, etc. And headless, because we knew there would be external consumers other than our UI that would be consuming our data. In the center there, you see 3 bolded bullet points. They were kind of around the core of how we designed the system. So CQRS, which we'll get into in a little bit, eventual consistency, and event sourcing. So those became kind of the foundation of how we designed the system. So the toolkit that we had decided on was obviously Scala and Akka. And 3 years ago, 2.5 years ago, Akka persistence didn't exist yet. So we started out with Event Source D, which was a wonderful library created by Martin Krasser, and kind of what we cut our teeth on in the entire journaling, event sourcing type scenario. And then ultimately we're in the process of migrating to Akka persistence. For our HTTP layer, we use Spray.io. For our database, Mongo, and then for our user experience, we used AngularJS and a really nice graphing tool that's very flexible, D3. So I kind of put this slide together, the 3 pillars, the triage of the architecture. I call them the 3 musketeers: event sourcing, CQRS, and eventual consistency. So to get into some of the understanding of the things that we learned with event sourcing, Event Source D, and Akka persistence, I'm going to go a little bit through what those terms are from our perspective. So event sourcing. Event sourcing is a very powerful construct. It's not new. It's been around for quite some time. But over the last probably 25 years, as relational databases kind of took the forefront of how we store our data, the notion of event sourcing or appending to your database kind of went by the wayside from a business perspective. So what ended up happening is a lot of modern businesses began to rely heavily on the relational model, and as a result, they ended up storing essentially current state, the last known good value of whatever a particular domain aggregate would be. And that has some implications in that primarily the one that really stuck out as a sore thumb for us was the auditing capability. So in order to address that, you have to apply different frameworks or additional frameworks, additional coding, and so forth. It also has deeper implications in regards to the actual value of your business data, but we'll talk a little bit more about that closer to the end of the presentation. So as I had mentioned, the reality of it is that was not always the case. This is not how companies had always looked at their data. You go back to the mainframe days with IMS, DBDC, and things like this. They viewed it a little bit different, more of an event sourcing way. And I think that this current state model, which I had mentioned, is kind of an effect of adopting relational databases. So if you take a look at some of the high performance systems of today's world, mission critical systems, they really don't store the data in a relational model. Specifically in the energy industry, we have something known as SCADA, which is System Control and Data Acquisition. Underpinning that system is a store called a historian, and that system stores it exactly the way event sourcing works. Everything is an append-only log, if you will. In a lot of cases, it happens to be a flat file, but still, it's done for performance because SCADA systems will be accessing and delivering data in millisecond time frames. So it was not always the case, this relational model for designing your domain. So what events are, they're kind of a natural way to reason about and capture behavior. And that's one of the first things you realize is you're looking at a particular domain and you're going to begin to observe it and understand it. Event sourcing comes in as a component that you can utilize to kind of capture everything that happens in a sequence of events, and from that you can derive behavior. You track this by, essentially recording an event or a transaction. And so when you look at the store, the persistent store, the database, you don't see a current state model like you might see in a relational structure. In order to access current state, the notion is derived from the sequence of events. And I think probably one of the best ways to understand that is to look at the canonical example for explaining this. So if you think about a mature business model, the notion of tracking behavior in a mature business model is something that is kind of a part of the DNA of it. And one of the easiest ways to reason about this is to think of a register at a bank, or you can think of your checkbook, if you will. So in that scenario, you'll see here in this little example, we have a number of credits and a couple debits. And each one of those is identified by a particular date, and there's a comment associated with it. But if you were thinking about this from a database perspective, and you were to look at the database table, if you will, because you can use a relational database with event sourcing, you would see a number of rows in the table which would represent the historical events that have occurred in relationship to this register. So each transaction that occurs is a delta, and it's recorded. In that particular example, I had a denormalized total. That's kind of like a nice to have. You don't have to do that. But to calculate, the delta is applied to the last known value, and that last known value can be trusted because it's a natural audit log. And then when you want to replay or you want to reconstitute a state, you can redo it at any point in time. You could do it for 2 weeks ago. You could do it for yesterday. You can do it for any point in time up to now. The journal, if you will, or the process is reconciled. It will ensure validity. And the great thing about it is it's a verifiable audit log. So auditing is baked in automatically. It's not an afterthought. It's part of the architecture, the structure, if you will. You can derive your current balance at any time, and state for that particular domain object is derived. And again, you can do this at any point in time. So that has some really neat implications. You can go back and look at your data. You can reanalyze it. You can reason about it in ways. It kind of has a little bit of a flavor of business intelligence baked in. In the old days, data warehousing, so to speak. You can look at your data from different angles, and you can play use cases against it and see what would have happened if this was the case. So events of themselves, you can look at them as notifications. They're a report of something that has already occurred, something that's already happened. The reality of that then means that an event, because it has already occurred, it cannot be rejected. The system must always process an event. And the way you would name an event behind it would be order created, past tense, or item added. And that will make more sense as we get into commands as well. So I think another way to look at this is to look at how this would be implemented in maybe a little bit more involved scenario, and you'll get to see some of the value behind it from a business perspective. So everybody is familiar with the shopping cart. It's something that we all use when we log into Amazon or what have you, and we purchase items. So in this particular example, we have a shopping cart here, and it essentially has 4 items that the customer is going to add to it. Item 1, 2, 3, and 4, 30, 15, 12, and $5. And then associated with that is going to be the shipping information, where the customer would like to have it shipped. And then this order is inserted into the event store as a stream of events in sequence. So if we look at it from a diagram perspective, some things that you'll notice is there's no total persisted, right? The total, again, is a derived concept, so we're not going to persist that. And we see a sequence of items here as distinct events. And then the order is then streamed into the database. So now, at some point in the future, if the customer decides, hey, I want to delete an item from my shopping cart before my order is shipped. We've done that. I've done that many times. I buy a bunch of stuff and then decide, hey, one thing I don't want to do is order this one particular item. So they log back in. The system is going to grab the particular aggregate, if you will, and it will then remove that item from the aggregate, and then it will append that back to the event stream. So from the database perspective, this particular delete is just considered as another event. If you're again looking at the journal and you were looking at the sequence of events, you would have seen those 4 items added. You would have seen shipping information added, and then the next thing you would see is this particular item removed. So when you replay that sequence of events up to that point in time, you'll see that the order now constitutes 3 items rather than 4 from a current state perspective. But in the data store, it's still every single thing that has transpired since the origin of the aggregate. So as I had mentioned there, this is the way that you derive current state as of what current state would be right now is by replaying the previous transactions. And there's some other things that we'll get into shortly from an Akka perspective, like how you design this particular model and so forth. I have some code examples. We'll go into that. But the structural representation of the data from a current state point of view is not persisted. Again, it's a series of transactions. And the nice thing that comes out of that is your current state model in your domain is not coupled directly to your storage mechanism. And so that gives you a great deal of flexibility. Everybody is familiar with the terminology CRUD, create, read, update, and delete. That's essentially how a monolithic model is built in a lot of ways, or a lot of times. So in an event sourcing perspective, there is no, you essentially have updates, right? There are no updates and deletes. Everything is persisted as an event. It gets stored or appended at the end of the transaction log, and the deletes, updates, modifications to the aggregate are essentially events that get appended. So the next thing I want to cover to discuss a little bit is the notion of CQRS, because that was an integral part of our process of embracing the whole Akka persistence and event sourcing concept. So, what is CQRS? Command Query Responsibility Segregation. It stems from a concept that was coined by Bertrand Meyer, and that concept is command query separation. Methods should either be commands or queries. So within a given object, you have all this type of stuff that you're doing, and typically that gets merged together in some type of aggregate or DTO or service. And so what his argument was is that when you do this, you should have distinct methods that do commands. You should have distinct methods that do queries. And as a result, the methods that are oriented towards queries should return data, and the methods that are oriented towards commands should change state but not return data. A query should not alter state. So in that scenario, it becomes really clear as to what is modifying state and what isn't. And when you're building these types of applications, and you have to deal with concurrency and stuff, you want to try to design it such that that type of stuff is very easy to reason about. Again, driving towards a kind of atomic or microservice-based reasoning just allows, it's a lot easier to test and think about. So Greg Young took it a step further, and essentially what he said was I want to not only split these out as separate methods, but I think they should be separate objects as opposed to just being separate methods within an object. And so as a result, this provides you with a pretty nice layout of how you can, one, reason about your system, and two, how you can deal with a lot of things like clustering and all these types of things. So in our particular scenario, we essentially had two sides of the coin. We would have one side that was essentially Akka microkernel, which would be one particular microservice oriented towards just processing of commands, journaling events, and so forth. And then that can be clustered and sharded and so forth. And then our store behind that can also be clustered and sharded as well. Then the other side of the coin was the read side or the query side. And on that side, you configure it the same way, except now you're going to essentially have this read side for your data. And the read side is an interesting concept because the way that you store the data is going to be stored in such a fashion that it's screen friendly. The read side can be recreated. So the idea behind the read side is there's no dynamic queries, and there's a whole lot to talk about there that we won't go into great detail today, but suffice it to say it allows you to optimize separately your writing concerns from your reading concerns. So the reason, obviously for that segregation is you can have an imbalance between the two sides. And when you have a single pipe that's going to do both, it becomes very difficult to do that. It doesn't really become good. It doesn't, reads and writes going through the same pipe, it doesn't work out very well, and you begin to run into problems. In this scenario, you're able to highly optimize both sides to provide what you want. This ties back into the reactive manifesto and the ability to be responsive for your UI, etc. So more atomic to reason about, and as I had mentioned, the read side ends up becoming easily recreatable. So that brings us to where this journey led us to after we began to understand all these concepts and we began to dig into the notion of things like event sourcing, CQRS, and eventual consistency. So that led us to Event Source D, which ultimately led us to Akka persistence. So what is Akka persistence? If you look at the definition on the Akka documentation, Akka persistence enables stateful actors to persist in an internal state so that it can be recovered when an actor is started, restarted after a JVM crash or by a supervisor or migrated in a cluster. So resilience, that's one of the key things that it provides us. But there's actually a lot more that Akka persistence provides. And this is where it got really exciting for us. So in Akka persistence, it will provide you with the ability to do commands. And so as a result, this is kind of the C in CQRS. It provides you the ability to persist events. That's obviously the E in event sourcing. It provides you a mechanism through something called a persistent view, which helps you construct your query side for CQRS, and then it also provides resilience, as I just mentioned. So if we take a look at Akka persistence from an event sourcing and a command side, the first thing that you have to take a look at is what is a command. So a command is essentially the notion of receiving a request from a client in the form of some type of behavioral action. And what this allows us to do is take that command and process it. It ties, I believe, more tightly into domain-driven design. Commands are requests. They're a request to say, hey, I would like to do something. I would like to take an action. And so they're more imperative in nature, so something like create order or add item as opposed to order created and item added. They're a request and mutate state. And as such, a command can be rejected. They represent an action that a client would like to take. And the commands by nature are more tuned for messages than DTO in a typical event source system. So they kind of fit right into place with the whole message passing event-driven type of scenario. The other thing that commands do is they also imply a task-based UI. So task-based UIs are something that is, I think, becoming very popular, and it gives you a kind of a new way to reason about how you want to present and project to your customers. As I had mentioned, they can be rejected, and they kind of protect from exposing internal state of your domain model. The other thing that they do is this entire scenario event sourcing and with commands is it really simplifies your repository layer. You can, with Akka Persistence, you have different journals. You can swap them in and out, and your data will still be persisted. So in Akka Persistence, we have a persistent actor that processes commands, and it will then persist these events. The commands come in the form of a message, and it will be processed by what is called a persistent actor. That command can be rejected, and it can be turned into one or more events as a result. So there's a notion that has two types of ways to do this. There's one called command sourcing, and there's one called event sourcing. And it looks like we have a couple of questions. What I'm going to do is get through the lion's share of this presentation, and I think some of those questions will be answered in that process. If they're not, then I can go ahead and answer those at the end. So here we have a persistent actor, and for simplified purposes, we have a command called create shopping cart, and we have a event called shopping cart created. And then we kind of have here in this slide, we have this immutable aggregate instance. So the actual shopping cart itself will be immutable. It's going to be a case class. So the next thing we see is we have this notion of state. And this is an internal construct, and it's immutable as well. Essentially what it will do is it will do a defensive copy as a change in state comes. And you'll see here down where we actually utilize the persistent actor, there's two ways to approach this construct, and this is how we did our domain model. Originally we didn't do it this way. Originally what we did is you can kind of think of our persistent actor as a service, if you will. So when we were using event source D, we would create a processor, and we would call it, say, for example, orders processor. And inside that, it would have essentially a collection of the orders that were being processed. So the challenges that resulted from that is, one is internally, where we're maintaining current state, we could end up getting quite a few number of aggregates. Fortunately, both Event Source D and Akka Persistence utilize snapshotting, so that resolved that problem to some degree. But I think the bigger problem is when you have your domain model, you really don't have an easy way to, you can still cluster, but what we wanted to do eventually was cluster the actual model itself, the actual domain model. So in this example, you'll see here I have the actual shopping cart itself as a persistent actor. So what that implies then is that as each shopping cart gets created, it in and of itself will be a persistent actor. And this fits right into the Akka sharding mechanism, where you can activate and passivate your different actors, or your different aggregates, if you will. So shopping cart extends persistent actor is actually, from a domain-driven design perspective, is an aggregate, an instantiated aggregate, if you will. And it will maintain only its current state inside, and that reduces the requirement for snapshotting significantly. you can kind of time them out. So if it's a shopping cart that someone's using currently, it will be actually be loaded in memory. But over time, when the customer's not, perhaps they log off or whatever, that particular actor will then expire. And the next time you need it, the customer logs back in, the system will then recreate it. So that's actually baked into the Akka Akka clustering and really sharding mechanism. If you're not using clustering, there's another way you can approach that, and I won't go into that in great detail, but you kind of have to implement kind of like a locator pattern, and you yourself are then responsible for activate and passivate of your actors and expiration and stuff like that. So we have this mutable state variable here for shopping cart. That's okay, right? We're inside the actor, so that's not going to be shared. And so what that represents at any point in time, as long as this persistent actor is loaded, that you'll have access to the current state. You're not going to have to hit the database to get it unless this actor wasn't loaded. And it's there, so it's real quick. You have easy access to it, etc. The one implication that this model has, as opposed to the other model that I had mentioned, the service-based model, is from a CQRS perspective, when you have the service-based model where you have a service persistent actor that has a collection of aggregates in it, you can actually access it directly in memory to get like a list of aggregates that you might want to action upon. In this particular model, you have to rely more heavily on the read side because you don't have a list of the aggregates. They're spread out over the cluster. They could be anywhere. And so in order to, say, get a list of shopping carts that I want to take a look at as maybe an administrator, I would pull that data from the read side. And we'll get into that in just a minute. So here's the actual processing of a command. So I have this command that comes in, create shopping cart. It's going to go through some type of validation mechanism called create. And as a result, it's going to fold over that. And one of two things is going to happen. A, I'm going to reject the command for some reason. Perhaps they didn't include their shipping data or what have you. And so therefore, I'm going to send a message back to the user, on failure return to sender. Or if it passes muster, then I'm going to essentially utilize Akka persistence through the persist command. It's going to persist that event. And as a result, from a partial function, it's then going to update our internal state. So for this particular aggregate that is residing as a persistent actor, you'll recall the state variable that I had shown you earlier. That will now be updated. We don't want to update the internal state until we've confirmed that the event has actually been persisted. And then I'm going to switch. I'm using become and unbecome here to switch my behavior of my actor. I'm now in created state, as you see right there. So now we get to the query side, and this is in this particular model where your aggregates in and of themselves are actors as opposed to the other way. The querying side becomes pretty important. So Akka persistence provides the notion of what is called a persistent view. And it's wonderful, right? It actually makes the third member of the triage or the Three Musketeers, eventual consistency, that now becomes configuration. You don't have to worry about dealing with that per se, and I'll show you what I mean by that in just a minute. So a persistent view will be associated with a given persistent actor. That persistent actor itself doesn't actually have to be running at that time. The persistent view will pull from the journal directly. And Akka persistence provides a configurable interval that you can say, hey, I want this persistent view to update every 5 seconds, every 2 seconds, whatever the case may be. And the actual view itself supports recovery and snapshotting and all that. So eventual consistency is one of those interesting concepts. It really is defined by the stakeholder. It's not the, the developer, if you will, in the sense that the business decides how soon they want that update to occur. Some businesses require millisecond consistent data. Others may say, hey, every 5 seconds is okay. That's fine. The one thing it does imply from your UI perspective is this is where task-based UIs come in. When you go ahead and you persist an event, more often than likely you're going to want to refresh the screen and display the changes to the customer. In a monolithic model where you're using CRUD and all that kind of stuff, that's strong consistency that's reflected pretty much immediately, assuming that everything is tuned. But in this kind of scenario, in a distributed system, it's going to become eventually consistent across the boundaries. So, but again, the business will determine. But from a UI perspective, put if your eventual consistency metric or requirements, milliseconds, then you may just be able to go to the next screen with no delay at all. So it's really driven by the business. So, so here's a view for our shopping cart. It extends persistent view, and you'll see that we have the persistent ID in there. Every persistent actor has a persistence ID, and the view is tied to that directly. And in the next part here, you'll see it supports snapshotting, so you can actually rehydrate your view based on snapshots, and it can recover from those snapshots. And the next piece that we get into here is the actual synchronization between the persistent actor and the persistent view. So you'll receive, in the form of a message, because this is an actor, a payload. And if that payload is persistent, then you'll be able to address that event directly. So you'll see there, if payload match shopping cart created, and then I have ... So in there is where you would reason about what you want to do on your read side. Do you want to just persist, basically a replication of that event? Probably not. You're going to have some type of current state construct that you want to derive here. You're going to do something, right? This is where your projections are going to be stored for your screens, or perhaps outside services that will be coming in and so forth. So you would do that. And then also you have just payload in general. If it's not persistent, then it's quite possible that this view could be receiving messages from another actor that's not a persistent actor. That may be important for us, for example, where we had different metrics coming in to define a graph for a customer. We would have 3 different things come in. One would be meter data, which would be considered persistent, but then we would also have weather data and pricing data that would come in that wasn't journal data. They were coming in from an outside service. So we wanted to kind of take all those things and then write them out to be manipulated later for the graph. So, and here's our eventual consistency mechanism. Akka persistence configuration provides you with the notion of an update interval. So that's going to tell the view when it's going to pull from the journal, and it could be 5 seconds, could be 10 seconds, could be 500 milliseconds. Again, driven by stakeholders and what the business needs are. So resilience, the R in Akka persistence, the design kind of gives you the ability to isolate failure, because now you're dealing with, especially if you're layering in the philosophy of CQRS and so forth, you have a microservice that you would have clustered, and it's got essentially a single responsibility for processing events for the particular domain that you're dealing with, or the particular aggregate, if you will. You have failover via clustering, that's part of Akka, and so forth. And then the great thing about it is your state is recoverable, right? So as we had seen in the slide earlier, you have the ability, depending on what you're doing, to reconstitute or rehydrate the state of your domain. you're not losing anything. So the nice thing about this is the way that persistent views are designed, you get these features on both sides of the CQRS fence, on the command side, which is what we would typically think of event sourcing, and on the query side through persistent views. So it's a wonderful toolkit that provides a lot of features that, quite frankly, are not easy to code, if you will, if you're trying to do this yourself. So here, the resilience part, again, you have the ability to, through the receive recover method, re-bootstrap the particular actor. So in the case of one of the challenges that we ran into when we had the service-based model, if you will, is we had so many aggregates in our collection that restarting, it could take a while. So that's when we started implementing snapshotting and cut that down. In this scenario where your aggregate itself is a persistent actor, the chances of having a zillion snapshots are not as likely. So it doesn't become quite a big of a problem. And again, the real power of this design is you're able to essentially distribute your domain model. So so there we see the snapshot offer, and it will go ahead and process that and spin the system back up. So I think the two things that are real important in this is two sides of the fence, right? Whenever we're designing applications, we have business concerns and we have technology concerns, and we want to try to get along as best as possible. So in this scenario, one of the things from a technology perspective is because it's an additive-only architecture and append-only log, it becomes really easy to distribute, right? You're only doing inserts. And then the other thing is a lot less locks to deal with, right? When you're dealing with a relational database and you're trying to horizontally partition, what key do you do that on and so forth. So in event sourcing, you essentially have, one key that you're going to deal with. But I think equally, if not more important, are the business implications. And that is when you're tracking customers' behavior or user behavior, you're tracking it from inception, right? As soon as you spin the system up, you're going to begin to track this stuff increment by increment. You can always answer questions because you from the origin of your system when you bring it up, you can just walk through the sequence of events and begin to answer questions. And the really neat thing about it is once you've identified what the events are and the commands are that you want to capture, you'll realize that, wow, hey, I can begin to answer questions that may not have been asked yet. So in that example with the shopping cart, if you were building this from a CRUD-based perspective, delete would just update current state. You wouldn't have the notion once that was committed that that item still existed unless you had implemented auditing. And so then you would have to go back and add it as an afterthought. And the problem with that is that once that is added, you can only do it from the point that it was added forward, whereas with an event source system, it's part of the scenario from the beginning. So it creates a natural audit log for you. So that's my presentation. I hope that was helpful for folks understanding some of the lessons that we learned as we went through there. And I guess we can open up for questions.
Yeah, thank you, Duncan. That was great. I really appreciate the presentation. It provided a nice foundation for understanding real-world Akka persistence use cases. So thank you. Looks like we do have a few minutes left for Q&A. So let's hop over there. So one of the questions here is how to handle sharding. Your shopping cart actor needs to be unique across a cluster, and that can be kind of hard if you have load balancing or high availability. Do you want to go into that? Can you dive a little bit deeper into that question?
Yeah, so I'll dig into that. In our initial model, we actually didn't have sharding. When we built this out, Akka clustering was just in its infancy. So we were not able to utilize that, but that's actually something that we're looking into now. The way that they're currently designing that is that as you, and again, there's more I have to dig into here to fully understand the model, but Akka clustering with sharding will actually allow you to distribute your domain model across the cluster. They tie into the shard key, into the, if I understand it correctly, into the persistent actor ID. But that is something that we're working on currently.
Great. Okay, hope that answered the question. Next question was, how do you model meter data? Do you use Akka persistence to deal with this kind of big data?
Yes, we do model meter data that way. So the challenge becomes in either scenario, whether you're using a service-based approach or you're using an aggregate approach, you're going to get a lot of meter data. That's just something that you have to embrace, do it through snapshotting. But that is probably the highest throughput area, and at least in the stuff that we have to deal with that has to be managed. So in the current model, my understanding is that is something that they're going to go back to and re-architect. But the current model is essentially the service-based approach, heavy snapshotting, because the in-memory collection can get quite large. So meter data is time series based data. I think that's standard stuff. And then to manipulate that for a customer perspective, especially from a graphing perspective, we just fire that event off over to the read side. And then the read side is going to take that and massage it and do whatever it needs to do with it to put it in a way that's ready for the screen.
Okay, cool. Thank you. We have lots of actually really great questions here. So let's maybe take one or two more, Duncan, and then maybe you can follow up with some folks as one-offs when we wrap up. Does that sound all right?
Sure. Yeah.
Okay.
So I can answer the Akka streams one. That was actually a mistake in the diagram. It's actually not Akka streams. It was just a persistence mechanism into the read side data store. So at the time that we had built that out, Akka views were not available. So in that particular instance, we used reactive Mongo to be asynchronous just to persist to the database. But Akka streams is the future of where we wanted to take a look at that, because we wanted to be able to stream data to the screen as opposed to, having to make a query and respond back.
Okay, cool. Thank you for touching on that. Are there any gotchas when deploying Akka persistence in production? Anything people should kind of be aware of?
So we worked with our cloud vendor. I think the whole architecture in and of itself is essentially built on top of the reactive manifesto type architecture, distributed microservice based. When you go out to your cloud vendor, whomever that might be, in our instance we use CloudBees, we had to do a lot of work with them up front to get them to kind of understand the way that we wanted the landscape to look, which in turn meant they had to open up a lot of different ports for us so our microservices could talk back and forth. So I think that in of itself is something that requires a lot of due diligence, and you have to make sure that you're working with a partner that responds correctly in an appropriate time and works with you. I think that aspect of it. Once you get beyond that, we essentially constructed our modules or microservices in SBT, and we would do atomic deployments, if you will, of each one. It works great. We didn't really run into any significant traditional deployment problems, if you will. I think it's just configuring the environment in production is the biggest challenge initially.
Thank everyone for attending this first half of Akka Days, and also thank you, Duncan. If people's questions were not addressed, Duncan will follow up with you directly afterwards. And as a reminder, this session was recorded, and we'll be sharing the slides with everyone as well as the recording in a day or so. So we're going to take a quick break, transition over to the next speaker. The folks over from Cake Solutions are going to be presenting tuning and monitoring Akka. So you're going to hear some hold music for a few minutes, and then we will get started at the top of the hour. We'll see you all soon. Okay, everyone, thanks for joining us for the second part of Akka Days. Our next presenters are from Cake Solutions. Jan Machacek and Alex Lashford are going to be presenting tuning and monitoring Akka. Excited to have them on board. Cake is actually a partner of Typesafe, so we always love to have them as presenters. Just in case you didn't join us for the first presentation, wanted to go over some brief housekeeping items. As a reminder, the presentations are all recorded. We're going to be making all the presentations available on our website and YouTube channel right after we wrap up. Look for those in a day or so. And if you have questions throughout the presentation, please just submit those into the chat box on the lower left-hand side of your screen, and we will get to those during the Q&A session at the end. With that, I'm going to go ahead and hand things over to Cake. Thanks, guys, for joining us.
So good morning again if you're listening to us in the US. Good evening if you're in the UK. Good night if you're in Asia. I mean, the sun truly never sets on the Typesafe empire, does it? So we're going to tell you about tuning and monitoring Akka, about our experiences and things that you should keep an eye on, and just some best practices along the way, tips from the battlefield, I suppose. And we'll take any questions that you'll have at the end, and we'll of course get to everyone. If we don't answer your question, don't worry, we'll get back to you in the next few days. So,
congratulations, you've made it.
We're waiting for a slide. There we go.
So, congratulations. So everyone loves your system. Your interactions increase. You're processing hundreds, thousands, tens of thousands of requests a second. You know, and you start to worry. Popularity starting to grow. You think, have we got everything we need to deal with this interest in our new application? So, Akka's 5 years old. It's a fantastic framework. Gives us the tool set to create scalable and event-driven applications. Hopefully these apps will follow the core principles of the Reactive Manifesto. But what happens when you've created the next Netflix? Unfortunately, Akka doesn't solve all of your woes of running in production. It's not a silver bullet. You still need to keep an eye on your stack and follow the key principles during your development. So in our talk, we're going to run through some of the basics of Akka in production and hopefully give you some tips and tricks as you embark on your production journey. So the question is, are you really ready for production? We'll revisit this question later on, but before we do, let's take a look at these basics.
So the basics. It is not, of course, Microsoft. Basics are that you need to be event-driven and scalable. So events in Akka are really messages delivered to your actors, and they are not really inconvenient and clunky method calls. They are actually truly asynchronous events that can arrive at any point, and your system must react to them. So this helps scalability, right? If you design a system whose components are loosely coupled and communicate through messages, it then becomes a lot easier to scale such system by simply adding processing nodes. So these processing nodes, think CPU cores. You've upgraded your Amazon machine. You have more computing power. Great. You could add more JVMs. You could add multiple network nodes. You could add sets of network nodes. Who knows? But what you may have spotted by looking at event-driven and scalable is that these are the two reactive traits. And so what we really want to achieve, what we really want to do, is to tune to achieve the remaining two. You want to be resilient and responsive. So, moving on, still keeping up with the basics. First thing, and this is Akka 101, but it bears repeating. Your actors should form hierarchies, and you only have very few top-level actors. Now that's really, really, really important, Because if you don't have actor hierarchies, how are you going to supervise your children? It's the supervision strategies, you see, that define how you are able to react to errors, how you are able to be resilient. So every time you create an actor, have it create its children and have it supervise the children and have it handle any potential errors that arise from the children by doing, either by recovering, that is, putting itself and its children to a state that is stable, the state before the exception. We're not talking about magically handling every exception. You know, this is not a Pokemon exception handler. This is a state, this is a code that gets you to a state before the exception happened. But second thing, right? You have hierarchies, you have supervisor strategies, so you can deal and isolate the failures, but you also need to configure the dispatchers, the routers, and the mailboxes.
And this configuration should be in a well-known place. You know, if the actor configuration needs some logic, there's some complexity around it, have it all in code. If the actor configuration is simple and can all be configuration-driven, let's keep it there. Just from a battlefield example, it is best not to mix the two types of configuration. Just don't mix the approaches. So it's also often tempting to send back a function that closes over the state as a response from an actor, but that is always a terrible idea. Ignoring for now the problem of sending the closed over variables and the function to some remote actor, this sort of horror immediately puts you in the raw Java concurrency world. So that's another key point, you know, encapsulate the state within the actor.
Okay, so we are waiting for a slide, but as soon as that reacts, we'll be able to move on. There we go. So you have a basic system that is hierarchical. You have actors form hierarchy. This is event-driven, which makes it easier to be scalable. You are resilient, and you are responsive. So, I mean, that's probably good, right? If you did all of this, all of the things that we told you now, you would be in a pretty good place. But it is, depending on what your problem is, depending on what types of problems you're dealing with, you may find it useful to tune things to achieve the best responsiveness and best resilience. So, the job is really to ensure that we configure the dispatchers, the routers, and mailboxes appropriately, depending on the type of load that your application is expected to handle. And better still, you would instrument your application to know rather than think as to the type of load that your application is going through. So, before we get into the nitty-gritty of everything that we wanted to tell you, let's explore what mailboxes, dispatchers, and routers do.
So, in the Akka world, the dispatchers define the mailbox sharing strategy and schedule the delivery of the messages between the actors. We have 3 dispatchers baked into Akka. So, the default, the one you get out of the box, this dispatcher sets an actor with its own mailbox. It's shareable amongst other actors, backed by thread pool or fork join pool, and is optimized for non-blocking code. The second type is a pin dispatcher, so sets each actor with its own mailbox, is non-shareable amongst actors, and creates a dedicated thread for each actor. This again is backed by a thread pool, and is optimized for CPU-bound intensive operations. So the third type we'll discuss is balancing dispatcher. So this sets one mailbox for all actors, shareable only amongst actors of the same kind, and again backed by a thread pool or fork join. So the mailbox holds the messages delivered to an actor. The dispatcher decides how actors share the mailbox, delivers the message to the mailbox, and schedules the actor's receive function. There are about 8 different types of mailboxes, but the general theme is that mailboxes can be bounded or unbounded. Again, unbounded is a terrible idea generally, and will only ensue pain when you come to production. But we'll touch on that later on. And a second grouping is arbitrary or prioritized queuing for these messages. So imagine you have particular messages going through your actor that you want to be executed more quickly, so you give those messages a higher priority. And the third type is the transient or persistent mailboxes. So there's plenty more detail of this in the Akka documentation. The thing we'll mention here, and many more times in the talk, again, is unbounded, is bad. So the last bullet point, routers. So the router manages and maintains its routees. The dispatcher delivers a message to the router, and depending on its routing strategy, decides how to deliver to one or more of its routees. So the strategies are round robin. As you would expect, if you had 10 child actors, you would route the first one to number 1, the first to number 2, the second to number 3. Once you got to number 10, it would then send the next message on to number 1. Random, as you would expect, will pick one of the 10 to send the messages to. Smallest mailbox, that's a little bit more complex. So that will monitor the rate at which the actors are processing these messages and look at the mailbox for each of those actors and send the message to the one under the least amount of load. Broadcast is another one. If you want to send a message to all of the actors of those 10, you can send one. Again, then scatter and gather first completed. A slightly more complex one built on top of broadcast. It will send the message out to all of the 10 instances, but then only process the one that comes back first, the response that comes back first. So now that we've discussed about routers, mailboxes and dispatchers, let's see how we choose the right one for the given problem.
Okay, so when we looked at the applications that we've written and that have made it into production, we discovered that we noticed, really, there was no discovery, that there are 3 classes of problems. The first one deals with number or string crunching. In our case, we admit it is mostly string crunching, so think translation of some XML into some other XML, and pulling some interesting data. Your applications could actually deal with some number crunching. So if someone's doing big data, hands up, yay, well done, you would be doing number crunching. Second class of problems dealt with I/O. So this is the usual boring input-output network communication, files, pipes. And a third class of problems, really, had to do with memory. How much memory is being consumed, and how do we go about allocating and deallocating it efficiently? How do we stop the application, in other words, from getting stuck under some memory pressure, either garbage collector pressure or actual pressure from the swapper. All right, so let's take a look at it. The first type of problem, number of string crunching. Alex, you know how to do number and string crunching, right?
So yeah, this is typically CPU-bound work. So there's no point in attempting to be somehow non-blocking. You know, the CPU is busy performing computation. It cannot do the work in the background and then magically send you a message when it's done. It's there being busy. So the ideal dispatcher for this type of work, you know, in our experience, would be the pin dispatcher. So backed by a reasonably sized thread pool. Remember, CPU-bound work feels like blocking I/O, but actually keeps the CPU hot. You want to avoid context switching. You want to keep the caches hot and prevent the CPU from entering sleep idle states. So if you've got lots of computation to perform, let's dedicate some resource to do that and ensure that it's being used as efficiently as it can.
Right, so the name implies the behavior, right? Pinned dispatcher pins a particular actor to a thread it allocates for it. And so you configure the size of the thread pool. Unfortunately, we can't give you a magical formula. This is the awkward thing. What will work on, say, EC2 C3 8X large, I'm probably making out the machine name by now, might not work just as well on the Rackspace cloud, not to mention Giant, which I believe is running Solaris. And that's all assuming that we are talking about x86 64 CPUs. If you are running on ARM, then the tuning of the thread pool becomes even different. But the rule still is, if you are doing number crunching, use the pin dispatcher and be aware of the fact that this will feel like blocking work. But it isn't. It is actually doing useful stuff. For the pointy-head people amongst us, this is exactly what you want to do. If you are paying for an Amazon machine, have it do stuff.
Exactly. Make the most of your allocated units of computation, and make sure you're making the most of the Amazon or the cloud provider of choice.
Absolutely.
The machines that they give you.
I/O. So,
this is file, network, pipe traffic, all potentially blocking. Non-blocking APIs that there are for many of these problems are not a golden hammer. You cannot just think, I'm using a non-blocking API, therefore I'm safe. All my problems have gone away. To be flippant, why do you think they say a network interface comes with a silly specification like 1 gigabit a second? It means that you shouldn't feed it more than 1 gigabit a second, and even that's just skimming the details. But let's not get too messy with kernel code and hardware. With non-blocking APIs, you should be aware of back pressure. So, what is back pressure? It's a mechanism that allows the downstream components to drive the flow of data. So, the concept in reactive streams is that downstream components must explicitly ask for more data from the upstream ones. So, if the downstream guys are feeling confident, they can say, easily request max value values, and then it's up to the upstream guys to satisfy that demand. If the downstream components are super cautious, they'll only ask for one element at a time, and the upstream components must comply with that demand and only give what the downstream component asks for. If you're using a non-blocking API appropriately with back pressure, be sure to configure and use appropriate timeouts to react to error conditions. Remember, the errors will come later, most likely to be delivered on a different thread. Same applies to timeouts. If your users are expecting a timeout within 2 seconds, it's useless to have a 60-second timeout on your HTTP call that you've only instantiated due to the user's request in the first place. So, finally, if you're using blocking calls, be sure to separate them into their own futures, actors, actor systems, ultimately threads. Your actors cannot block, otherwise you're risking the health of your entire actor system. So the third and final section is memory. So, use bounded mailboxes.
I'll repeat it again. Use bounded mailboxes. It's really, really important. If you don't, I'll DDoS you before you even know it.
So, if your application generates too much pressure from the GC, if Jan's trying to DDoS you, the performance will degrade. But there's nothing you'll be able to do about it. In extreme or simply naive cases, you can make your application, appear completely frozen just by sending your actors too many messages. So first off, and this applies to any production-ready Akka system, always use bounded mailboxes. Here we go again. If you do not, it's possible to kill your Akka system by forcing out of memory errors, or to generate so much GC pressure that your application will be completely unresponsive.
Yeah, and it doesn't just apply, of course, to the GC pressure. You could actually allocate so much memory in your Java program that you will kill your operating system, and it will start paging so much that your user space program just won't get the chance to run. So, you think, well, how would I get that? Surely I tune my JVM with the appropriate XMS and XMS and XMX and what have you parameters. Well, you could consider using direct or off-heap memory structures. So think that the various byte buffer APIs. Incidentally, if anyone's noticed, this is what Spray is using. So in Spray, the HTTP request will carry the byte buffer of the entity, because Spray is saying, well, actually, I will never look inside unless you want me to. I don't have to look inside the HTTP body. I can just give you the byte buffer. If you want to deserialize it into some sort of JSON marshaller, fine. I'll bring the bytes into the managed bytes on the JVM. But where I'm heading is that, sure, you could run your JVM and give it a gigabyte of heap space, and then you can allocate 20 gigabytes of heap memory, at which point your operating system will be pretty unhappy. But the worst thing is, and I think this is our final point, and we've seen it so many times, that memory or garbage collector pressure will make your application die with a whimper. It won't be a bang. It will slow down. and it just will not be pretty. So you want the bang. You always want the bang. Remember, resilient, right? You want to be resilient and responsive, and event-driven and scalable, but that's assumed, that's by the by. So if you want to be responsive, you need to be able to react to a message that arrives to you. If you want to be resilient, you need to get to a place that happened before an error occurred. If you are not doing the things that we've just talked about, it will become harder and harder for you to achieve these two other traits. So, well, that was the easy bit, right? So you can follow all of the advice that we gave you, and your code will probably be pretty good. But sometimes things really aren't ideal, and Alex has had a lot of battles with code that doesn't follow the ideal scenario. This is code that's been given to us, and we had no choice about it.
Exactly. So here we mean integration with libraries that block threads that once they fail, they keep failing, and services that you know or suspect are not scalable. So what really categorizes these things? So as you would expect, not responsive. So APIs or libraries that are not responsive, you bulkhead those, separate those and give them a dedicated thread pool and executors. So you want to identify and isolate the bad bits or the bad integration points. So APIs that are not resilient. So you want to bulkhead failures, define good supervisor strategies so that you can have an informed decision of being able to recover to a state that you can do things. Not scalable. So this is, you want to implement flow control, back pressure for reporting, or a hard circuit breaker. So if everything goes wrong, you can go, actually, we're going to stop integrating with this API, but it's not going to affect the rest of our application. Things like this should always be considered, and it's just, that's how things are. You have to integrate with existing software in your organization, or, there might only be one library that does the thing that you're trying to solve. It'd be nice to make all of this reactive, and but one needs to pick the battles. And so rather than trying to fix the world, an easier way and a more doable way is to isolate the problematic areas and try to be nice to those services that can't keep up with your scalable, reactive, high performance system. So think how important the concept of back pressure is. It's far better for your system to know what its dependencies can cope with, rather than sudden failures or have to have a hard circuit breaker.
So as Alex is suggesting, there are two main strategies really that we take. So
these are bulkheading and back pressure. So a little bit of history. So we hear bulkheading sort of often through our presentation and lots of others, but the principle comes from shipbuilding, where you would typically bulkhead or divide parts of the hull and aim to prevent the whole ship from sinking due to damage to a single section of the hull. This idea is easily applied to the architecture of an Akka application. You need to isolate the CPU intensive and the blocking I/O so not to bring down the application to a standstill, so that you can keep that reactive and high responsiveness. The second concept is back pressure. So as we said previously, it's far better for your system to know what its dependencies can cope with than to deal with a big bang, encapsulate the slowness, and allow that function to self-regulate its consumption rate. Reactive streams, as implemented in Akka streams, for example, provide non-blocking reporting and dealing with back pressure. On top of that, reactive streams provides a very convenient DSL to express, the various transformation steps. So that's going to be particularly interesting.
Right. So here we are. I think we have the tools by now. We know how to build a reactive system. We know what patterns we should follow, and we have these strategies really to deal with code that doesn't quite fit our neat world. So what we're going to do now is to explore in a slight more detail the three kinds of non-dependencies that we would have. So non-responsive, non-resilient, and non-scalable. And we'll try to give examples from the code that we have written that illustrate where you might meet such dependencies and what you might then do with it. So let's start with first of the not so ideal things, which is not responsive. So again, hang on for the slide transition. Nearly.
Goodness.
There we go.
There we go.
Zombie hammer. There we go. Brilliant. So, not responsive. It is so by responsive, what do we mean? Oh, well, it means that your code sends a response within some expected timeout. And the response could be even I'm too busy, or there's an error, or slow down. But at least the sender knows that the thing it sent the message to is alive. Now, if we send no response at all, so we are not responsive, then the sender cannot make any reasonable decisions. So, okay, well, what's the first culprit, really? Blocking I/O, right? That's the first thing that springs into anyone's mind. In blocking I/O, all sorts of horrible things happen. First of all, you consume threads. So that in itself is bad, because you can't just keep increasing the number of threads in your operating system without any limits. Threads represent overhead for the kernel. Now, what's even worse is, not only, suppose you decided, oh, well, I'll throw 10,000 threads at it. Let's see how Linux can deal with it. Sure, great. So you're now spending more time in kernel time because of the management, and your threads aren't doing anything useful. You see, if the OS, the kernel, knows that a thread is blocked by, say, an I/O operation, and if it knows that all threads are blocked in an I/O operation, it might decide to be very clever with the CPU management. It might decide to put it into a reduced power state. Now, once the I/O operation completes, the blocking I/O operation completes, remember, the CPU wakes up, but everything from that moment on, every memory access, every operation takes so much longer. And the second culprit that I have here is synchronization. Notice the spelling. So don't try to paste that into your IDE. It won't work. You'll need the Z. But it doesn't matter. What we mean is it's a way of attempting to tame your parallel processing. So in Akka, if you ever write await.ready or await.result, you're doing it wrong. I would almost suggest maybe you could use a Scala-style warning, an error. So the shameless plug for a Scala-style plugin that I've been working on for IntelliJ IDEA. But it doesn't really matter. It's bad code. So educate your programmers. If you are dealing with futures or zip them. Don't await for them. And for those management-style listeners, if you're on the call, raise your hand so we can disconnect you. But no, I'm only joking. We're fine. If you are not using the cloud machines to their full potential, you're wasting money. You're wasting money at phenomenal rates. So, an example that Alex has from the battlefield, he's not going to even mention the usual stuff of, I don't know, a JDBC driver that is blocking. There was one which you could say was just sloppy code. But here's an example. It was just an example of how blocking code might actually look completely innocent. Blocking doesn't mean I/O necessarily. So to Alex's thing, what did you do?
Yeah, so remember that number or string crunching can feel like blocking. So in one of our systems, we found a badly configured jack speed marshaller. We were needlessly creating and dropping instances, which ate a lot of CPU time, and essentially made our system less responsive. So how we identified that, we had some monitoring, and which really gave us some visibility, which we'll touch on in a few slides down the line. But essentially, we saw that the time in the on-receive handler increased, the number of available threads decreased, and there was just something very odd happening in that actor that we didn't expect, to happen. There was what we thought was blocking code happening. Oh, we must have got some, we've got someone's putting a weight in there and we haven't caught it, or there's things like that need to be addressed. And wait for the slide to change.
I'm waiting for the slide. Yes.
So monitoring definitely helps with things like that.
Okay,
So,
moving on. Slide has changed. Another less than ideal scenario, ignoring the sock sandals, is code that's not resilient. I'll shut up, Alex.
So resilient means the ability to get to a state where you were before the exception. So not resilient, cannot recover from an inconsistent state on its own. So, you know, that's like a third-party library or a legacy library that you've got that, you know, once it gives an exception, it always gives an exception. You know, for example, maybe hibernate or replace any other library you've used that you've, you know, have had sleepless nights over is damaged. You know, every subsequent call to that will be broken too. So here a supervisor strategy will probably solve it. You know, maybe reinitialize the hibernate session or restart the affected children. Although it could be worse. You know, maybe the error is in a static initialization block. You know, that you had no option other than to do that. You know, it runs when the class is loaded in the JVM. Now, even a supervisor strategy cannot save you. You know, unless you want to do some magic with some class loading, but you probably don't want to go there. So just propagate the error up. You know, kill the JVM, or, you know, which is fine. Remember, we're scalable, we're resilient. You can fire up a new node, or, you know, remember these nodes are stateless. You know, everything just should work. If you ensure, you know, and if you're unsure, you know, in your development pipeline as you go into production, you know, introduce Chaos Monkey. You know, let the Chaos Army drop things. Let's see what happens. And decoupling your actors and your act systems and identifying the bits of code that are going to be problematic can really help you deal with problems in production.
Next point that I think is really interesting, and we had that problem with, as it happens, JPA, is failures spreading to other parts of the system. So think lazy marshalling, or in our case, JPA. So we were sending an instance of, well, not to give you too much detail, let's pick a user class. User is a fairly obvious thing. So we were sending an actor an instance of the user class. When the actor received it, it called the roles accessor, and it got a JPA exception. So what I'm trying to say is that simply implementing some sort of Pokemon exception handler strategy won't save you. You need to be in your actors to be able to react to failures, and you will be only able to react to them through some supervisor strategy. If the supervisor strategy is not sufficient, as in you cannot recover within the bounds of the JVM, stop the JVM, system exit -1 will do, even though you should probably allow the failure to hit your actor system, which will do it for you. But your goal is to get to a state where you are stable again, the state before the exception. And if that means killing part of your actor system, so restarting a particular subtree of the actor system, so be it. If it means restarting the entire JVM, so be it. And if it means restarting the entire virtual machine, or so be it, fine. But don't just whimper along in an inconsistent state. The next problem, and this is my favorite error message, and we'll have to wait for it. This is so frustrating. Too many errors, please close some errors to continue. Not really scalable, right? Probably not even resilient. But anyway, so this is where you find yourself relying on a component. But by that I mean, think a payment gateway, or maybe
some translation service,
we had an airline that shall remain Irish and nameless. You suspect that service cannot scale. So it's your responsibility. Maybe you signed a piece of paper that says, we will only send it 10 requests per second. It's your responsibility to be nice to that component. So you need to implement your own flow control. However that looks, it could be your own stab at simulated back pressure, because remember the component that you are talking to doesn't tell you anything back. It doesn't say slow down. the behavior from your point of view is working, 503. Or working, my manager gets a phone call saying, you are DDoSing my system. Stop. So, ideal scenario, you would have flow control in your system. But even if you don't have that, do implement some sort of circuit breaker. So a circuit breaker is essentially a big red button. Think a Boolean, if in, then make the call. If not allowed, then don't make the call. It is designed to stop the requests reaching that component. Now, of course, that means that you will have some sort of management API for your application. We completely skimmed that, but it turns out to be very, very important. It could be as simple as another set of REST endpoints. Maybe your internal endpoints could have, you would do a post to /stop the world, perhaps. Or you'd expose some JMXN beats. Anything. Now, what is important to remember is that Akka and maybe Akka Streams gives you the tools. So we talked about the different dispatchers, we talked about the supervisor strategies, the way to bulkhead your application, to isolate it into different futures, different actor systems, different actors and maybe different actor systems, but you just have to be aware. You have to know what to do. Which brings us to the next slide. How do you know, really?
Exactly. So, tell me again, how is everything fine in production? What's happening inside your application? How do you know that everything, is running well and you've got visibility? So you should be looking to lift the lid, on our apps and shine the light on the black box that is Akka sometimes and get some much needed visibility. So we want to know, do we have any hotspots in our actor system? Are the message queues getting too big? Are the messages spending too much time in queues? Is the mean time in the on-receive too high? Do we have enough threads? Are those threads being blocked or used efficiently? So monitoring gives us the insight into the performance and flow of the application, allowing us to see these hotspots and areas of poor performance, increasing our visibility to what's occurring. So everyone's aim is 24/7 uptime, preventing the big boom. How do you know that something's broken in time to do something about it? It's inefficient, it's insufficient to monitor 500 errors. You want to have some time before that 500 to do something about it.
That's right. And before we get into the actual error monitoring, we talked about tuning of your Akka system. You actually need to see what is happening inside. Exactly.
It's invaluable to see, when you put in your performance testing, you have monitoring going on, you can see, which are the slow bits, which don't work, which need optimizing for production, so that in your release strategy, when you get to the performance testing part, that you can react to the poor areas and fix those problems.
Sure thing. So what are the types of things that we would like to monitor? And we won't go into any huge details. I think we talked about it at Scala Days, and there are plenty of other talks that will give you the insight. But on the highest level, right? The first rule is to monitor just enough information, and that's sometimes tricky. For a small fee, we will advise you, of course. But no, in all seriousness, if you monitor too much, then you slow down the system being monitored. If you monitor too little, well, you're not getting enough information so you can make a sensible decision. So, in the app that we've written, this was a big price aggregator, we found that it was sufficient for our purposes to monitor actor creation and destruction, the message types that are arriving, their rates. So how many HTTP requests are we getting in? How many flight price comparison messages are we sending out? What are the failure rates? By that we mean our own problems. So how many times do we throw an exception in the actors on receive? And we wanted to monitor the performance at the actor level. How long does the on-receive handler take to handle the message? Now we correlate that with the queue sizes at maybe the local or the actor level. So if on-receive takes too long and the queue is increasing and the CPU is being really busy, then we can make some sensible decisions about it. And of course, by that, when we monitor the CPU, we monitored the number of available and running threads in thread pools. The only problem, and the fundamental problem with monitoring, is that if you do wire in a monitoring tool, you cannot allow the monitoring tool to bring down the system being monitored. Don't allow the monitoring system. The monitoring system has to be the last man standing. You have to know that things are failing right until the last possible moment. So we looked at a couple of monitoring options, didn't we? During development,
yeah,
as well as production.
Exactly. So as we said before, so there's three things that we'll talk about here. So Typesafe console. So that's very much a development-focused monitoring tool. It's really great. I'd recommend setting it up. Especially if developers, you're running, especially if you're running performance tests locally or running tests locally, you want to see what's going on.
Imagine it gives you microsecond resolution on Windows. Okay, no, never mind. Let's stop.
And enough Windows. We were going to be nice. So, yeah, that's aimed at development and can really provide improved visibility of your application, especially for your development team. So the second one, probably the best, or maybe not the best. That's just a shameless plug. So there's a reactive monitor. So that's something that we wrote here at Cake to scratch our own itch. Really, we needed something that was lightweight and configurable, and that could monitor these things that we said previously in the slide, and not impact the performance of the system, or at least go unnoticed. So there's lots of interest in this field. So a fairly new one is the Camon IO. I don't know.
I'm foreign.
Yeah.
I can mispronounce.
So again, that's lightweight, configurable. Interestingly, all these three work by using aspects. They use low time weaving to instrument the Akka code to get application and information. So all three things, they're all well worth a look. They've all got the last two have got multiple integrations, so you can pump out to StatD or CodeHail metrics or dtrace if you're on Solaris. So there's lots of visibility there. I mean, from the reactive monitor, we were pumping that up to Datadog, which gave us a nice UI, and that proved.
We are now moving to Graphite, aren't we?
We are now moving to Graphite as well as an internally hosted solution, and that's working really well.
So we are nearing the end. There are things to remember. On a slightly cheerful note, we will end. Wait for the slide. Suspense is killing me, so to speak. So remember, be event-driven, which helps scalability. Then ensure that you remain responsive through non-blocking APIs and bulkheading of the blocking calls. Take care of back pressure and memory pressure. If you're not doing these things, you will either hurt your responsiveness and resilience, or you will appear not responsive and not resilient. Consequently, it will be really hard to be scalable. If your system cannot report back that it's in trouble, you cannot react to it. Any scaling strategy will fail. As Alex said, it is really insufficient to monitor HTTP 500s. It's too late. You need something a bit better. If you are building your Akka system, use your system's hierarchy and recover at the appropriate point of the hierarchy. So, a small subset of the actor system, of the actor tree, entire JVMs, clusters of JVMs, who knows? It is far better to go out with a bang. So think system exit -1, 2, -42, then whimper along. The second thing to remember is good measurement is good science. Good observation is good science. First of all, you really want to come home and say to your partner that you've been doing really complicated science all day at work, but more importantly, you actually need to know and measure what's being monitored, what is happening in your system. That will give you the insight into what type of load your application is really experiencing. Is it number crunching, which feels like blocking? Is it blocking I/O? Are you consuming too much memory? So much so that your JVM, that you're killing your JVM with too much garbage collector pressure? Are you allocating so much off-heap memory that you're killing your operating system? So all of these things you will discover through monitoring. We've given you the tools. Finally, and it's not a moan, it's a statement of fact. The Akka 101 applications don't provide production-ready configuration or style. And that's not okay, it is a criticism, but it's through no fault of their own. We've written a good few activators, and it's really hard to show in a concise package something that scales. And then more to the point, if I downloaded the Typesafe activator, and then was presented with, it's going to cost you $20 just to press run to have a look, I probably wouldn't do it. Nevertheless, there's plenty in the Akka documentation and in the resources online that should hopefully point you in the right direction. So, Alex, any other observation?
No, I think that really covers it. It's take a look at what we've presented in the slides, and the Akka documentation is really spot on and can provide you a good, some good information to start breaking up your application. So just make sure you follow the key principles we've outlined, and hopefully you will create the next Netflix.
Absolutely. So finally, slides there if you want to see some of the speaker notes, because the slides don't contain that much text. Press S, follow our tweets, and Murphy of DevOps, and we'll leave you with that. We'll be happy to take questions.
Yes, thank you so much, Alex and Jan. That was great. You both have so much valuable and tremendous experience in the battlefield implementing these things. So, I encourage everyone to listen to some of Jan and Alex's other talks. You mentioned the Scala Days one, but you guys can head over to Parlays and watch that. It's really great too. So yeah, let's take some time for questions.
Sure.
All right. So, question here: how do I prevent actor fragmentation? To process a business request, I need to load 10 domain objects, and they're on 10 different nodes. The network latency might really hurt me.
Well, first of all, is it really? If you say it is required to load it onto all those 10 different nodes, if it is an absolute requirement and you have to shift the data across the network, then there is not a lot you can do to avoid it, as you say. What I would look at is the serialization protocol. So when we were dealing with particularly the JAXB messages and big XML messages, as an example, that was actually hurting us quite a lot. If you are interested, if you go to Martin Thompson's Mechanical Sympathy blog, he writes about very compact binary protocol to exchange your data. So if the problem is in the size and in the efficiency of shifting these objects across the network, then consider reducing the message sizes, make it a binary protocol, and reduce the amount of time you have to spend, the amount of computation you have to spend to pack the messages and unpack them on the other side.
Great. I hope that helped. The next question is: how do you monitor a system that has thousands of actors? At times, this individual has more than 10,000 lightweight actors in a system. So, is there any advice that you can give?
We would normally, so in Reactive Monitor, as an example, but this applies to any old anything, the monitoring tool should allow you to filter and decide which actors you want to monitor. So sure, you've instrumented your Akka bytecode, which means that any actor instance is potentially monitorable, but you might not want to monitor every single message. And you might also not want to monitor a certain actor path. If you are using routers, that might be really helpful. So you say you have 10,000 actors. Is it really every single actor is really, important in where it sits? Or is it the case that you have, 100 different actors, but you have 10,000 instances which are being routed? And so depending on what you have, you would choose a different strategy. Alex had to implement code that doesn't monitor and doesn't deliver the messaging output of every single message. So in reactive monitor, what he would say is deliver to the monitoring tool every 5th message. But what we mean is increment counter by 5. So actor receives 1, 2, 3, 4, 5 messages, and then it sends a monitoring message out that says, I have 5 messages.
Again, yeah, that was really to make sure that the monitoring tool wasn't taking up I/O resource to post out.
That's right.
You don't want where at all possible, your monitoring tool to take any resource that could be used for actually doing the computation of your real application.
And in our case, as it happens, we were using StatsD, which is a very lightweight protocol over UDP. But we had to implement particularly that. We were generating so much UDP traffic that we were getting some pretty unhappy results from the kernel, and simply the number of interrupts we were causing on the network interface. So, yes, reduce the number of messages.
Yeah, so you reduce the number of messages. You can see by type, mailbox time on, averages of time on receive. If you should be able to see enough from the type of messages and the granularity that we offer in the console, and I'm sure Command IO does as well.
Yeah, so I think that's all we can say.
Yeah, I think so. Also, there was a sort of a sub-note there that the Typesafe console is unusable in that case. Yes, I can agree with that. That our
we killed the system with the Typesafe console.
Yeah, that's exactly what happened to us. We realised that we wanted to see this information. So we loaded up Typesafe console. We set it up locally on development machines. We're running 1 a second through, and everything was.
And the client loved it. The user interface was fantastic.
Looks great. It was all looked dreamy. All looked really good. Got great visibility. You could see things. You could even at that point we identified bits weren't quite right. So then we tried to set it up on the performance server hosted in the cloud, and we were hammering hundreds of requests a second, and then all of a sudden, really weird stuff kept happening, and we started to look in the logs, and the application just wasn't really doing anything. It just didn't have any resource. We thought, this is odd. Then we looked in the system logs of the machine, and yeah, the Typesafe console, the connections to the database had gone through the roof. It was just eating memory. So yes, the Typesafe console just wasn't fit for that purpose, and hence said it's really good for development, but you need to move to a more lightweight version. So, the reactive monitor or Command IO. I think I've given it about 12 different names now. Someone would like to correct me at some point.
It was a consequence of monitoring too much.
Yeah, exactly.
Monitoring too much, you will get visibility over everything, but it will be difficult. If you are implementing a monitoring tool, try to pick one that collects information not just from the actor system, but also from other components. So you want to monitor OS processes, you want to monitor CPU load, free memory, swap space, that sort of thing. Ideally, this would all be delivered over some unified, or at least viewed, right? It doesn't have to be delivered over unified, through some unified mechanism, but it needs to be visible under some unified mechanism.
So we mentioned briefly that we used Datadog, and that gave us the ability to have this nice one graph, one dashboard overview of the application. So we got machine metrics and application metrics all presented nicely on one thing. Since then, we've then moved to Graphite, and that's then we've used dashing and things to plug into this data to pull in metrics and this monitoring information. There are a couple of things that have been really useful to us.
Okay, let's have a few more.
So, is there a list of metrics that reactive Akka monitoring will push to StatsD?
There is.
There is.
Short answer.
Yes, on the README, hopefully. I think of the is that hosted up there? I'll tweet out the if we can't find reactive monitor from Googling, I'll tweet out at the end the location of the GitHub and it's on the README. And if
and
it's
we have
not,
PDF documentation that we have actually published.
Yeah.
We'll do a blog post summarizing this entire talk. So, and if we, in fact, let's do this. If we have any more questions, we'll take a few more questions now. But the ones that, Laura, you're going to send it to us over Excel. If we find answers that we think are really, really helpful for everyone, if you don't mind, you know, we won't publish your name or anything. We'll put it on our blogs. I hope people will find it useful.
Yeah, I think that's a good strategy. Yeah, that sounds like a good idea.
Yeah, so
yes, which one?
There's a follow-up question, which is related. So they tried to use the reactive Akka monitoring, but had trouble sending data to StatsD. Looking at the code, they've eagerly-eyed noticed that it's got the StatsD, the Datadog StatsD client. So there was a little bit of vaporware that we discussed at Scala Days. It is almost ready to push out, and there will be a pull request this weekend, I promise, that will sort out that.
It's a Datadog extension. It just formats the.
It adds another bit. It adds another bit to the
datagram.
It's a very straightforward fix that I'll be doing for our own thing. I just haven't published it to the main repo, so I will fix that.
We promise, and it's recorded.
It's been recorded. It's on the internet forever. So.
Okay, one more.
One more. Okay, so when using bounded mailboxes, what happens when the mailbox is full? And senders are trying to send a message. Blocked all messages go to the dead letter office. What if those bounded mailbox actors are pulled by a router?
That's a good question. So it all comes back to supervisor strategy. You will be told that a message could not be delivered, and as a supervisor, you will be forced to handle it. So this is essentially you'll get an undelivered message. It will be sent to the system's event bus, I think. So you can react to it in reactive monitor. You'll see this was undelivered, and you should be able to. Your supervisor strategy should handle the situation somehow, right? And now this is where it gets really awkward. This is the notion of scalability. So Akka promises to be scalable, and I had a very similar question on Akka streams recently. How do you deal with it, right? So you're reporting back pressure, or you're reporting undelivered messages. How do you then scale, right? At some point, you will get to a situation where the messages are arriving at such a rate that you cannot deal with it. Well, remember, scalability means that, and reactiveness means that you can send a message to something else saying, I'm in trouble. So one way of handling this situation in your supervisor strategy would be say, okay, maybe I'll create more actors. That's one thing, right? So I'll create a few more routines and see what happens. And then suppose you're still getting extremely high load and your messages are still, the mailboxes are still getting full, even the mailboxes of the actors that you've now created. So you need to have the monitoring component that says, this is looking really bad. I need to create a new node of this application that can process it. And sure enough, okay, let's be clear about this. At some point, your application will fail. Unless you are the biggest application on the internet, right? So you are either the biggest application on the internet, in which case you can kill everyone else, or overload anyone else, or something will overload you. And the only strategy that you have available is to, first of all, measure and find out how your application behaves when it does fail, be able to do something reasonable about it, so supervise your actors, and thirdly, have something that reports back that something bad is happening. In case of the price aggregation system that we built, it's a similar story. We have essentially a dashboard. We have expected load. That says when we are running a TV ad, we know that in the next 5 minutes, what will follow is 300% of the usual load, or even worse. If somehow, through some series of unfortunate events, the load comes to 1,000%, we will not be able to handle it that quickly. We will scale up, absolutely, but it will take time. And during that time, we need to remain responsive. So even the user that comes in such a high load, makes a request to our system, we expect our system to even send back a message saying, I can't do it now. I'm too busy. That's far better than having just a spinny thing on the website that says, no, sorry, broken, or a 503. So that's the general strategy that you.
Do we have any time for one more, or are we out?
I think we can take one more and then we'll wrap up. Sound good?
One more.
Okay, so what's the best way to create back pressure in Akka? So exceeding the bounds of the mailbox goes to deadlock. How to deal with the back pressure actors, which chat between themselves without leading to deadlock.
We'd have to look at that.
Yeah.
Why do you have to pick a question that we don't know? We don't have an immediate answer to. How annoying! How annoying! So let's see. We did try Akka Streams, but that's not quite the question that you have. Now Akka Streams. Okay, let's see how Akka Streams works. Maybe we can sort of deduce it. So that takes the DSL, the flow DSL, and then through the materializer, it constructs actors that represent this flow. And the actors need to have a two-way communication. One that goes forward, that's the messages coming in, and the backward, which is the back pressure. So what we're going to have to do, Alex, is to look at the code and write a blog post. I don't think we can answer that one. Honestly, why do you have to pick that one as last?
All right. Well, I think following up in a blog post is a good strategy. Go into more detail anyway. Yeah. Well, thanks, guys. That was great. And if anyone had difficulty with audio or with slides, as we mentioned, it was recorded, and you have the slides available. I sent that out to everyone in the chat box. So look for the recordings in a day or so. Tomorrow we're going to have sessions by Derek Wyatt and by Mike Nash. Really looking forward to those.
Yeah,
kind of just as a great. Just as a wrap up, we like to sponsor these webinars. I think it provides, we hope at least, great content to the community and listeners. At Typesafe, we provide subscriptions, consulting, and training around Akka, Scala, and Play. So anything we can do and our partners can do to help you be successful, we always like to hear from you. So feel free to reach out to us through a Contact Us form on our website, or you can always shoot me an email. My email is laura.masterson@typesafe.com. And we hope to see you again tomorrow and on future webinars. Thanks again, Jan and Alex.
It was our pleasure.
Yeah. Cheers, guys. Thank you.